Edge AI, Intelligence at the Edge. I am Dr. Rajiv Mishra, working as professor in the Department of Computer Science and Engineering, Indian Institute of Technology, Patna. So, the contents of this lecture. So, before that, let us see that Edge AI has two parts, namely second part comprises of intelligence at the edge, and the other part is for that is edge intelligence for edge computing. So, this part we are going to cover in this edge AI, that is intelligence at the edge, how this intelligence, that is AI, machine learning and deep learning derived intelligence, how that can be put on the action at the edge, that is very close to the source. So, in this particular topic, we are going to cover the contents that comprises the background for intelligence at the edge for edge AI. That is, first we will go and see the review of deep learning, then how this optimizing artificial intelligence for the edge we are going to cover. Then in that we are going to see one of the latest state of the art, the technique called knowledge distillation, and finally we are going to cover the federated learning, that is how we are going to enable the intelligence at the edge. So, let us review the deep learning. So, if you see that particular artificial intelligence comprises or covers machine learning, and machine learning covers representation learning, and representation learning in turn covers the deep learning. So, the deep learning is a subset of machine learning, and together they are subset of artificial intelligence. So, in early days of AI, the field rapidly tackled and solved the problems that are intellectually difficult for human beings, but relatively straightforward for the computers. These are the problems that can be described by the list of formal and mathematical rules. A computer can be made to reason about the statements in the formal languages automatically using logical inference rules. This is known as knowledge based approach to the artificial intelligence. The rules are hard coded in the program. For example, Deep Blue, the chess playing computer developed by IBM, is primarily considered a rule based AI system. However, the complex problems that humans can perform intuitively, such as recognizing spoken words or faces in the images, cannot be described as hard coded rules, or is often quite difficult to do so. A person's everyday life requires an immense amount of knowledge about the world. Much of this knowledge is subjective and intuitive, and therefore difficult to articulate in a formal way. These difficulties faced by the systems relying on hard coded knowledge suggest that AI systems need the ability to acquire their own knowledge by extracting patterns from the raw data. This capability is known as the machine learning. So, the introduction of the machine learning allowed the computers to tackle the problems involving the knowledge of real world and make decisions that appear subjective. For example, a simple machine learning algorithm called linear logistic regression can determine whether to recommend a product or a service to a customer or not. An algorithm called naive Bayes can separate legitimate emails from a spam email. However, it is known that the performance of simple machine learning algorithms depends heavily on representation of the data they are given. Each piece of information included in the representation of the input is known as the feature. For example, to determine which product to recommend to a visiting customer, one might consider various features such as customer's age group, their preference towards a particular brand, their profession, etc. Logistic regression learns how these features of a particular customer or the service correlates with various outcomes such as customer buying the product or not. However, it cannot influence the way that the features are defined in any way. Many artificial intelligence tasks can be solved by designing the right set of features to extract for that task, then providing these features to a simple machine learning algorithm. However, for many machine learning tasks, it is difficult to know what features should be extracted. One solution to this problem is to use machine learning to discover not only the mapping from the representation to output, but also the representation itself. This approach is known as representation learning. So, learned representations often result in much better performance than can be obtained with hand designed representations. When designing features or the algorithm for learning features, our goal is usually to separate the factor of variation that explain the observed data. For example, suppose that we would like to write a program to detect cars in a photographs. Now, we know that the cars have the wheels, so we might like to use the presence of the wheel as a feature. Unfortunately, it is difficult to describe exactly what a wheel looks like in terms of pixel values. A wheel has a simple geometric shape, but its image may be complicated factor of variation such as shadows falling on the wheel, something obscuring part of the wheel, and so on. Many of the factor of variation can be identified only using sophisticated, nearly human level understanding of the data. In the speech recognition task, the speaker's accent is one such factor of variation. It can be difficult to extract such high level abstract features from the raw data to obtain a representation as to solve the original problem. Deep learning is the subfield of the machine learning that focuses on artificial neural networks and their application in solving such a complex problems. Deep learning solves this central problem in representation learning by introducing representations that are expressed in terms of other simple representations. That is to say, deep learning allows us to build complex concepts out of the simpler concepts. Each layer in a deep neural network can learn a simple feature of an input. For example, in a car recognition model, some layers can learn to detect the edges, while others detect the corners and contours. The higher layers can then learn high level features such as individual parts of the car like wheels, etc. The field of deep learning has witnessed a significant advancement in the recent years, contributing to breakthrough in various domains such as computer vision, natural language processing, and reinforcement learning. Now, optimizing models is the requirement of providing the intelligence at the edge. So, there are two important techniques called model compression and acceleration techniques, which often uses the following categories of the tasks, that is parameter pruning and sharing, low rank factorization. So, low rank factorization, then transport compact convolutional filters and knowledge distillation. These are all optimizing the model so that the intelligence at the edge can be realized, and that is what is the important concept we are going to understand. Therefore, let us see this particular details. So, large deep neural networks have achieved remarkable success with good performance, especially in the real world scenarios with large data. Because over parameterization improves the general performance when a new data is considered. However, the deployment of deep models in the mobile devices and embedded system is a great challenge due to the limited computational capacity and memory or the resource constraints of the devices. To address this issue, model compression was proposed to transfer the information from the large model or an ensemble of models into the training a small model without a significant drop in the accuracy. So, the knowledge transfer between fully supervised teacher model and a student model using unlabeled data is also introduced for semi supervised learning. Overall, the model compression and acceleration techniques can be divided into the following categories. So, that is the first category is called parameter pruning and shearing. So, these methods focus on removing inessential parameters from the deep neural networks without any significant effect on the performance. Now, this category can further be divided into model quantization. Model quantization was introduced by Wu et al. In 2016, and the model quantization is a technique used in the neural network to reduce the memory footprint and computational requirement of a model by representing its parameter and activations with lower bit precision. So, benefits of model quantization include reduced model size, then decreased memory bandwidth requirement, and faster inference, making it especially valuable for deploying the deep learning on the edge, mobile devices, or scenarios where computational resources are limited. That is called model quantization. Then model binarization is a technique in the neural optimization where the weights of the models are constrained to binary values, typically +1 and -1 or 1 and 0. Instead of using floating point or a fixed point numbers to represent weights, binarization involves converting them to the binary values, usually +1 and -1. This process significantly reduces memory requirements and computational complexity of the model, making it more suitable for deployment on resource constrained devices. Binarized neural networks often use binary activation functions such as binary step function or variants of the binary sigmoid or a binary 10H functions. The third category of parameter pruning and shearing is called parameter shearing. This was proposed by Han et al. In 2015 and Wang in 2019. So, parameter shearing is a technique used in neural networks where certain parameters are shared across different parts of the model. This can be beneficial in various ways such as reducing the number of parameters, enhancing generalization, and enabling the network to learn patterns more efficiently. Convolutional neural networks are the classical example of parameter shearing. In convolutional layers, the same set of weights, that is kernel or the filter, is used to scan the entire input image. This shared weight scheme allows the network to detect local patterns, that is the features regardless of their location in the input space, making CNNs effective for image recognition tasks. Then weight tying is another technique that involves sharing weights between different layers or parts of the neural network. For example, in sequence to sequence models, the weights of the encoder and decoder are tied, reducing the number of parameters and improving the model generalization. Low rank factorization is a technique used in neural networks to approximate weight matrices by decomposing them in a low rank matrices. This approach is motivated by the idea of reducing the number of parameters in the model while retaining its expressive power. Low rank factorization can be applied to various types of layers in a neural network, such as fully connected layer or convolutional layers. These methods identify redundant parameters of deep neural networks by employing the matrix and tensor decomposition. The use of low rank factorization can lead to more computationally efficient training and inference, as reduced to the number of parameters requires less memory and computation. For example, singular value decomposition (SVD) is a common method for low rank factorization. It expresses a matrix as the product of three matrices W is equal to U, sigma, V and transpose. So, U and V are orthogonal matrix and sigma is a diagonal matrix of a singular values. To achieve a low rank approximation, one can truncate the singular values and corresponding columns U and V. For convolutional layers, low rank factorization can be applied to the convolutional kernels. This reduces the number of parameters in the kernel and can lead to more efficient models. Tensor factorization techniques such as Tucker decomposition or CP decomposition can be applied in the convolutional layer context. Low rank factorization can act as regularization technique, preventing the model from overfitting to the training data. By limiting the capacity of the model through reduced number of parameters, it may generalize better to unseen the data. Now, transferred compact convolutional filters. These methods remove inessential parameters by transferring or compressing the convolutional filters. Compact convolutional filters typically refer to a small size filters or kernels used in convolutional layers within a neural network. These filters have a smaller spatial extent compared to the larger filters commonly used in traditional convolutional neural networks (CNN). The use of compact filters is motivated by various factors, including the desire to reduce the number of parameters in the model, enhance computational efficiency and capture local patterns in the input data. Knowledge distillation. Knowledge distillation, these methods distill the knowledge from larger deep neural network into a smaller network. So, knowledge distillation, the learning of a small model from the large model is formally popularized as knowledge distillation. That was coined by Hinton et al. In 2015. In knowledge distillation, a small student model is generally supervised by the large teacher model. The main idea is that the student model mimics the teacher model in order to obtain the competitive and even the superior performance. The key problem is how to transfer the knowledge from large teacher model to a small student model. Basically, the knowledge distillation is composed of three key components. The first is called knowledge, the second is the distillation algorithm, and third is student teacher architecture. The general teacher student framework for knowledge distillation is shown over here. So, this is the teacher student framework is shown for the knowledge distillation. Shown in the figure. Now, knowledge distillation is a model comparison method in which a small model is trained to mimic the pre-trained larger model or an ensemble of models. So, the vanilla knowledge distillation uses logits of large deep model as a teacher knowledge. These activations neurons or a feature of intermediate layers can also be used as the knowledge to guide the learning of the student model. The relationship between these activations neurons or the pairs of samples contains rich information learned by the teacher model. In distillation, knowledge is transferred from teacher model to the student model by minimizing the loss function, in which is the target is distribution of the class probability predicted by the teacher model. Specifically, knowledge distillation is accompanied by minimizing KL divergence between the prediction of a teacher and student. So, this method of knowledge distillation was first proposed by Christian and then generalized by Jeffrey Hinton. So, this training setting is sometimes referred to as teacher student, where large model is called the teacher and the small model is the student. In distillation, knowledge is transferred from teacher model to the student by minimizing the loss function, in which the target is the distribution of the class probability predicted by the teacher model. Specifically, knowledge distribution is accomplished by minimizing the KL divergence between the predictions of teacher and the student. So, KL divergence, that is called Kullback-Leibler divergence, is a measure of how one probability distribution is different from the second. Expected probability distribution. So, the expression is given by this equation 1. So, the key points of KL divergence is that non-negativity, that is KL divergence is non-negative and is equal to 0 if and only if P and Q are the same distribution. Non-symmetric or a non-commutative KL divergence is not symmetric. The order of P and Q matters. Not a distance matrix, KL divergence is not a true metric, as it does not satisfy the triangle inequality. So, this particular fact, with this we are talking about now the knowledge distillation. So, we define the teacher network T and a student network S. Typically, the networks can produce the class probabilities that converts the logits Z I computed for each class into the probability Q I by using the softmax function. So, we define the class probability P I, which is generated by the teacher model T, and Q I, which is generated by the student S network correspondingly. Then K D loss can be given by this equation number 3, which is shown over here, where P x and log of Q of x I, here that C denotes the number of classes and tau is the temperature parameter, V and Z indicates the logits generated by the teacher model and the student model respectively in the knowledge distillation. If we regard the class probabilities P as the soft label, then KL loss can be regarded as the soft max cross entropy. It is not hard to derive the relation between the cross entropy and KL divergence. So, given P and Q, we define the entropy as H, and now then you can write down the equations 5 and 6 using that formula. Now, in knowledge distillation, we optimize the student network that can mimic the teacher network. Then we rewrite our loss function using the KD loss function using the equation number 7. Here HP is independent of theta, that is entropy. The optimization goals then becomes the argmin of theta, that loss function of KD loss function is obtained using equation number 8. Then we can find the optimizing KD loss is equivalent to optimize KL loss in the knowledge distillation setting. In the knowledge distillation, knowledge types, distillation strategies and the teacher student architecture plays a crucial role in the student learning. Now, we shall discuss different strategies of knowledge for knowledge distillation as follows. The first is response based knowledge, feature based knowledge and relation based knowledge. So, response based knowledge, the knowledge modeling usually refers to the neural response of the last output layer of a teacher model. The main idea is to directly mimic the final prediction of a teacher model. Here you can see the logits and then the same thing will be used in the distillation. So, in response based knowledge usually refers to the neural response of the last output layer of the teacher model. The main idea is to directly mimic the final prediction of a teacher model. The response based knowledge distillation is simple yet effective for model compression and has been widely used in different applications. Formulation. So, given a vector of logits Z as the outputs of the last fully connected layer of a deep model, the distillation loss for response based knowledge can be formulated using this equation, where this indicates the divergence loss of logits. Z t and Z s are the logits of teacher and the student respectively. Now, for example, the response in the object detection task may contain logits together with the offset of the bounding box. In semantic landmark localization task, that is the human post estimation, the response of a teacher model may include a heat map of each landmark. So, to easily understand the response based knowledge distillation, the benchmark model of vanilla knowledge distillation, which is the joint of the distillation and the student loss, is given in this particular figure. Note that the student loss is always defined as the cross entropy between the ground truth level and the soft logits of the student model. The effectiveness of the soft targets is analogous to the label smoothing or regularizers. However, response based knowledge usually relies on the output of the last layers. For example, the soft targets, and thus fails to address the intermediate levels supervision from the teacher model. This turns out to be very important for representation learning using very deep neural networks. Since soft logits are in fact the class probability distribution, the response based knowledge distillation is also limited to the supervised learning. For example, the most popular response based knowledge for image classification is known as soft targets. So, specifically soft targets are the probabilities that input belongs to the classes and can be estimated by softmax functions, where Z I is the logits of for the ith class and temperature factor T is introduced to control the importance of each soft target. Accordingly, the distillation loss for soft logits can be rewritten as this equation. Now, feature based knowledge. So, deep neural networks are good at learning multiple levels of feature representation with increasing abstraction. This is known as representation learning. Therefore, both the output of the last layer and the output of the intermediate layer, that is the feature maps, can be used as the knowledge to supervise the training of student model. Specifically, feature based knowledge from intermediate layers is a good extension of the response based knowledge, especially for the training of thinner and deeper networks. The intermediate representations were first introduced in FitNets. Romeo et al. Has published in 2015 to provide hints to improve the training of the student model. The main idea is to directly match the feature activations of teacher and student. To be specific, attention map can be derived from original feature maps to express knowledge. The attention map was generalized by researchers in 2017 using something called neural selectivity transfer. So, the feature based knowledge, there the output of intermediate layers, that is the feature maps, can also be used as the knowledge to supervise the training of the student model, which forced the feature based knowledge distillation. It is the improvement of response based knowledge distillation. Knowledge modeling. Generally, the distillation laws for feature based knowledge transfer can be formulated. So, generally the distillation laws can be formulated by this equation which is shown over here, where f t x and f s x are the feature maps of the intermediate layers of teacher and student models respectively. The transformation function phi t and phi s are usually applied to the feature map of the teacher and students. Student models are not in the same shape. So, the loss function f is called similarity function, used to match the feature maps of the teacher and student, and it is shown here in this particular figure. So, knowledge modeling, for example, proposed a feature based knowledge distillation using attention mechanism, especially the student network learns the attention information from the teacher. For example, considering CNN layer and its corresponding activation tensor, which consists of C feature planes with special dimensions h and w, an activation based mapping function f with respect to that layer takes the input the above 3D tensor A and outputs a special attention map, flattened 2D tensor defined over special dimensions. Another example is specifically in this work. There you consider the activation based special attention maps. So, relation based knowledge, in both response based and feature based knowledge use the outputs of specific layers in the teacher model. Relation based knowledge further explores the relationship between different layers or data samples. Formulation. So, in general, distillation laws of the relation based model, relation based on relations of feature maps, can be formulated by this particular equation. Now, offline distillation. Most of the previous knowledge distillation methods work offline. So, in offline knowledge distillation, knowledge is transferred from pre-trained teacher model into the student model. Offline distillation, the whole training process has two stages. The large teacher model is first trained on the set of training samples before distillation. The teacher model is used to extract the knowledge in the form of logits or the intermediate features, which are then used to guide the training of student model during the distillation. Online distillation, both the teacher model and the student model are updated, and the whole knowledge distillation framework is end-to-end trainable. Self-distillation, the same networks are used for teacher and the student model. This can be regarded as a special case of online distillation. Distillation methods now combine the knowledge distillation and ensemble learning, a graphical diagram for the proposed method to train a new thin deep learning network by student network by incorporating multiple comparable teacher networks. The method consists of 3 losses, including label prediction loss, dark knowledge loss, and relatively similarity loss. The incorporation of multiple teacher network exists in 2 places, one in the output layers while averaging the soft end output targets, the other lies in intermediate layer by determining the best triplet ordering relationships. Distillation methods, here the label protection loss is a simple softmax cross entropy loss, relative similarity loss is triplet loss, dark knowledge loss is ensemble KD loss. Now, given M teacher network N1, NT1, NT2 and so on up to NTM and one is network NS. Now, we can have this L final using this particular equation, where H means entropy function here and Ws indicates the parameters of the feature extractor Xi in this particular case. So, distillation methods combined knowledge distillation and cross modal learning architecture. We train the CNN model for the new image modality like depth images by teaching the network to reproduce the mid-level semantic representation learned from a well labeled image modalities such as RGB image for modalities for which they are paired images. So, distillation methods, so the proposed scheme for learning rich representation for the images of modalities. MD T indicates the function that maps to the same dimension, and we measure the similarity between the representation using appropriate loss function. So, distillation method combined the knowledge distillation and data free compression. So, the proposed model compression pipeline, a model is trained in a data center and released with some metadata. Then another entity uses the metadata to reconstruct the data set, which is then used to compress the model with the knowledge distillation, and finally, the model is deployed in a smartphone. Coming to the federated learning. Federated learning is also called a distributed machine learning. This was the term which is coined in 2016 by the Google researchers. We have already seen some real world deployment by the companies and researchers for large scale IoT devices. Several open source libraries are under development, such as PyShift, TensorFlow Federated, Fate, Flower, Substrata. Federated learning is highly multidisciplinary. It involves machine learning, numerical optimization, privacy and security, network systems and hardware. So, the standard setting in the machine learning considers a centralized data set processed in a highly integrated system, but in the real world data is often decentralized across many devices. Sending the data to the cloud for centralized machine learning may be too costly. For example, self-driving car are expected to generate several terabyte TBs of data a day. Some wireless devices have limited bandwidth. The power data may be considered too sensitive sometimes, such as medical reports. So, we see growing public awareness and regulations on data privacy. Keeping control of the data can give a competitive advantage in the business and research. In 2016, the term federated learning is first coined by Google researchers. In 2020, also we have seen some real world deployment by the companies and researchers. Federated learning is multidisciplinary. It involves machine learning, numerical optimization, privacy, security, networks, systems, and so on. Federated learning about decentralized data. Now, federated learning aims to collaboratively train a machine learning model while keeping the data decentralized. So, you can see the data is there wherever it is being generated, enabling the devices to learn from each other. That is, machine learning is brought close to the net, is brought close a network of nodes, and all the nodes with their own central server, but instead of sharing the data with the central server, we share the model, and we do not send the data from the node to the server, instead send our model to the data. For example, here the data is trained and this becomes the trained model. So, only the model will be shared with the servers. So, you can see that at all the nodes they will keep their own data, and training the model, only the trained model is being shared to the server, data is not shared in this particular manner. Now, it uses the algorithm which is called gradient descent, and the procedure starts with the initial values for the coefficients or the coefficient for the functions. These could be 0 or a small random value. So, the cost of coefficients is evaluated by plugging them into the function and calculating the cost. So, now we need to know the slope, so that we know the direction to move the coefficient values in order to get the lower cost in the next iteration, that is called the delta, derivative of the cost function. We can now update the coefficient values. The learning rate parameter, that is alpha, must be specified, that controls how the coefficients can change on each update. So, coefficient is equal to coefficient minus alpha multiplied by data. So, this process is repeated until the cost of the coefficients is 0 or close to 0. It does require you to know the gradient of your cost function or the function you are optimizing. So, let us see about the gradient descent algorithm in working. So, gradient descent algorithm uses this particular equation. So, gradient descent is the most basic and most used optimization technique. Is used heavily in the linear regression and the classification algorithms. Backpropagation in the neural network, federated learning also uses gradient descent algorithm. Gradient descent is the first order optimization algorithm, which is dependent on the first order derivative of a loss function. It calculates that which way the weight should be altered, so that the function can reach a minima. Through backpropagation, the loss is transferred from one layer to another layer, and the model's parameter are known as weights are modified depending on the losses, so that the losses can be minimized. The advantages are easy computation, easy to implement, and easy to understand. The devices train the generic neural network model using gradient descent algorithm, and the trained weights are sent back to the servers. The server then take the average of all such updates to return the final weights. So, the federated learning is a category of the machine learning which moves the processing over the edge nodes, so that the client's data can be maintained at their locations. This approach is not only precise algorithm, but also a design framework for edge computing. Federated learning is a method of machine learning that trains a machine learning algorithm with the local data samples distributed over multiple edge devices or the servers without exchange of the data. This term was first introduced in 2016 by McMahon. Federated learning distributes the deep learning by eliminating the necessity of pooling the data into a single place. So, in federated learning the model is trained at different sites. So, that you can see they are trained at different sites and then the parameters are being sent to the central place. This method and then federated learning the model is trained at different sites. This method stands in contrary to the other conventional techniques of a machine learning, where the data sets are transferred to a single server, and to more traditional decentralized techniques that undertake the local data sets. So, take finding the functions that is in the model training. So, given the training data sets sometimes containing n input output pairs. So, the goal of this deep learning model training is to find the parameter w such that the average of p of y is maximized given x I, that is the maximizing of 1 by n, that is all n data sets, all n pair of input output pairs, which is equivalent to the minimizing the loss function. So, the basic component for the loss function is given here in this particular sample. So, deep learning model training. So, given one sample pair, that is x 0 y 0, the goal of deep learning model training is to find the set of parameter w to maximize the probability of outputting y 0 given x 0. So, for training data set containing n samples, the training objective is to minimize that f is the loss of the prediction on x I y I. So, finding the function that is about the model training, given one input sample x 0 y 0, the goal of the deep learning model training is to find the set of parameter w to maximize the probability of the outputting y 0 given x 0. So, here you can see in this particular figure. So, that algorithm which is being used in the federated learning is called federated averaging, FedAvg. So, federated averaging considers k clients are indexed by k, v is the local minimum mini batch size, and e is the number of local epochs, and nu is the learning rate. So, this is the algorithm which server executes, and this is the algorithm which client updates at their end. So, at first the model is randomly initialized on the central server like here, and at each round the random set of clients are chosen. For example, this is chosen random. Each client performs a local gradient descent. Steps the server aggregates and sends the parameters to the server, and server aggregates the model parameters submitted by the client, and then it will be distributed at all across. Now, federated averaging is IID. So, IID means independent and identically distributed. Independent and identically distributed. Now, in federated learning, each client trains its model decentral. In other words, the model training process carried out separately by each client. Only learned model parameters are sent to the trusted center to combine and feed the aggregated main model. Then the trusted center send back the aggregated main model back to these clients, and this process is circulated. A simple implementation with IID, that is independent and identically distributed data, to show how the parameters of the 100 of different models are running on different node can be combined with federated average methods, and whether this model will give the reasonable results. Now, this implementation was carried on an MNIST data set. Now, the MNIST data set contains 28 by 28 pixel grayscale images of numbers 0 to 9. MNIST data set does not contain each label equally. Therefore, to fulfill the IID requirement, data set was grouped, shuffled and then distributed so that each node contains equal number of each labels. A simple two-layer model can be used to classification process using federated averaging, since the parameters of the main model and the parameters of all the local models in the nodes are randomly initialized. All these parameters will be different from each other. So, the main model sends its parameter to the nodes before the training of local models in the node begins. So, the nodes start to train their local models over their own data by using these parameters. Each node updates its parameters while training its own model. After training process is completed, each node sends its parameter to the main model. The main model takes the average of these parameters and sets them as its new weight parameter and passes them back to the nodes for the next iteration. The above flow is for one iteration. This iteration can be repeated over and over to improve the performance of the main model. The accuracy of centralized model was calculated as approximately 98%. The accuracy of the main model obtained by federated averaging method started from 85% and improved to 94%. So, you can compare that the centralized model can give you the accuracy of 98%, whereas the federated can go up to 94%, which is quite acceptable. Now, Apple personalizes Siri without hoovering up the data. So, the tech giant is using the privacy preserving machine learning to improve its voice assistant while keeping your data on your phone. It relies primarily on the technique called federated learning. It allows the Apple to train different copies of the speaker recognition model across all users' devices using only the audio data available. It then sends the updated model back to the central server to be combined into the master model. In this way, the raw audio of the user's Siri request never leaves their iPhones or iPads, but the assistant continuously gets better at identifying the right speaker. In addition to federated learning, Apple also uses something called differential privacy to add a further layer of protection. The technique injects a small amount of noise into any raw data before it is fed into the local machine learning model. The additional steps makes it exceedingly difficult for malicious actor to reverse engineer the original audio files from the trained model. So, federated learning training. So, these are connected devices. Let us say that we have the cluster of 4 devices. From the 4 devices, there is only one central server that has an untrained model. We will send the copy of the model to each node. You can see each node will have this copy of the untrained model. Now, each node would receive the copy of that particular model. Now, all the nodes in the network has an untrained model that is being received by the server. The untrained model. Now, in the next step, we are taking the data from each node here. It does not mean that we are sharing the data. Every node has its own data based on what is going to train the model. Now, each node, you can see that has a different trained model based on that local data available at the nodes. So, each node is training the model to fit the data that they have, and it will train the model accordingly to its data. Now, the server would combine all these models received from the nodes by taking the average. Here it will take, or it will aggregate all the model received from the nodes. Then the server will train that central model. This model will now be is now trained by aggregating the model from each node. It captures the pattern in the training data on all nodes it aggregated one. Now, once the model is aggregated, the server will send the copy of the updated model back to the nodes here. So, everything is being achieved at the edge. So, no data sharing is done, which means that there is a privacy preservation and also very less communication overhead. Now, federated learning challenges is that there is a system heterogeneity, that is the size of the data, computational power, network stability, local learner learning rate, and the expensive communication, that is communication in the network, can be slower than the local computation by many orders of magnitude. So, federated learning challenges is dealing with non-IID data, that is independent and identically distributed. So, learning from non-IID data is difficult or slow in federated learning, because each IoT device needs the model to go in a particular direction. Now, if the data distributions are very different, learning a single model which performs well for all IoT devices may require a very large number of parameters. Another direction to deal with non-IID data is thus to lift the requirement that the learned model should be the same for all IoT devices. Instead, we can allow IoT K to learn A, that is a potentially simpler. When local data sets are non-IID, federated learning suffers from the client drift. To avoid this drift, one must use the fewer local updates. So, preserving privacy, that is machine learning models are susceptible to the various attacks on data privacy. Membership inference attacks try to infer the presence of a known individual in training data set. Reconstruction attacks try to infer some of the points, and federated learning offers an additional attack surface. So, data distribution. So, in distributed learning, data is centrally stored, that is in the data center. The main goal is just to train faster. We control how the data is distributed across the workers. Usually, it is distributed uniformly at random across the workers. In federated learning, data is naturally distributed and generated locally. Data is not independent and identically distributed, and it is imbalanced. Additional challenges that arise in federated learning is enforcing the privacy constraint, dealing with the possibly limited reliability, availability of participants, achieving robustness against the malicious parties. When to apply federated learning is when the data privacy is needed, bandwidth and power consumption are the concern, and high cost of data transfer. And when not to apply the federated learning is when more data won't improve your model, and when additional data is uncorrelated, and when performance is already at the ceiling. So, the applications of federated learning is in the area of predictive maintenance or industrial IoT, smartphones, healthcare, that is wearable, drug discovery, prognostics, and enterprise or the corporate IT such as chat, then issue trackers, email, etc. Conclusion: in this lecture, we discussed about what is a knowledge distillation, different types of knowledge distillation, methods of knowledge distillation, and understanding of federated learning, different uses of federated learning, and we have also covered this as the background for performing the edge AI, that is the intelligence, how to bring intelligence at the edge. Thank you.